Good afternoon, dear students. Can you hear me?
Yes, I hear. Good afternoon, teacher.
Okay, thank you. So let's start today's lessons. Okay, let's share the screen.
Hocam, before starting, can you inform us about exam? How many questions it will be?
Exam will be around 4 questions. And you need compass, you need ruler, and you need, to draw. And I expect also that you send after the exam the papers. You have to scan and send to me. But also you will answer. The answer is also will be included in the question. And selection, you have to see, multiple choice.
Is it gonna be
The
PDF?
question will be multiple choice, but I need also the exam paper, huh?
Okay.
At the end of the exam, let's say in 15 minutes, you have to scan and send to me. Okay?
Via Blackboard, right? Not email.
Yes, via Blackboard, yes. Or
Okay.
email.
Thanks.
Okay. So let's share the screen. Okay. In our last lessons, we have been started to talk about the velocity, and we were discussing the chapter velocity. So we will continue with velocity. Okay, here. So the velocity analysis. So maybe just a brief information about what we did in last lessons regarding the velocity. So we said velocity is important mechanism, and therefore, in some cases, we need to calculate the velocity.
Hocam.
Yes. Can you hear? And can you see?
Yes. Hocam, şeyi sorabilir miyim? Teorem ödevi ne zamanaydı acaba?
Nasıl?
Teori ödeviyle alakalı mail attınız da ne zamanaydı acaba? Onu sormak istedim.
I guess 7 of April, as far as I know. Or can be 10th. Can be 10th also, 10th of April.
Sisteme mi yükleyeceğiz hocam? Nereden teslim edeceğiz?
Efendim?
Sisteme mi yükleyeceğiz soruları?
Bana mail olarak göndereceksiniz.
Mail olarak, tamam. Teşekkür ederim.
Mail olarak. But let's so I send the email to you. Let's see that. So I need the homework in a certain content, and therefore let's see that. So then I will share with you now. Okay. Not that. Okay, here. So this is content, okay. So you see the content of the home, or the rules for let's say the rules for the homework. Here I sent already to you via email. So first of all, the problem itself will be transferred before the solution. So I have to see first the question, problem as problem, then what is given, and what is desired or to find, and the step of solutions, plan for the solution, and the solution step by step. It must be followable and understandable. So not write just a piece of paper something and send as a homework, and it must be, let's say, let's say how do you say, a good format. Huh? I expect a good format.
Okay hocam. Thank you.
Okay.
Deadline will be 10th or
10th. Okay, is for no problem.
10th April.
So official format, huh? Not something you not something you write on a piece of paper and then just take a photo and send as a homework. This is not acceptable. So please pay attention for that. Okay. So then we can continue. So we said the velocity.
I just have a note for the homework.
Yes, this is the note for homework.
The homework itself gonna be handwritten?
Yes, can be handwritten, but it is
Okay.
it must be readable, understandable, followable, and not because if you cannot understand, I cannot follow it. Huh?
Okay.
So therefore I write these steps you have to follow. And first of all, the problem. What is the problem? So there's a display the problem, and then the what is given and what is expected, or what is to find, and then you make the plan, the solution. So first I will do that, and second and third and so on, and you solve the problem. So this is the methodology to solve a problem, and I really interested to force you to work with this methodology. It is very important for you, not for me, but for you is very important. For me, it must be understandable, because I cannot spend lots of time and to see what is it and what does it mean and so on. It must be still a format. Huh? Okay.
Okay.
So thank you. So okay, the speed we said. So the speed velocity is very important mechanism, because we design the mechanism to do certain works or realize certain motion or transfer certain power in a machine or with other mechanism maybe. And this velocity is very important. Later, next chapter will be the acceleration. We will talk about the acceleration, velocity and acceleration, very important. Then if you have time, then I'm also interested to talk about the force of inertia coming from the velocity for acceleration and all those things, because you you will be engineer, you will become engineer, and then if you design something, so you have to be able also to make technical calculations. So the speed, so velocity analysis involves determining how fast certain points on the links of a mechanism are traveling. So velocity is important because it associates the moment of a point on a mechanism with time. So time is also important, cycle time and so on. We discussed in our last lesson a little bit about, I informed you. So often the timing in a machine is very critical. So that means the cycle time. So how much time the machine is using for a single product to produce it. That's the cycle time, we call it. So especially in the mass production, so the cycle time is very important. Okay, so then we said, okay, we are now studying the rigid body motion. Since a link of a mechanism is a rigid body, so we are dealing with rigid bodies in mechanism, and therefore, what is the motion of rigid body? And we said the motion can be divided in those parts, part of rectilinear motion or curvilinear motion, on pure rotation, or general plane motion, and so on. And also here, we started with a simple example, linear velocity. That means linear motion, linear velocity. So this is a part here, you see, and let's use the laser pointer here. Here we have the here joint, and it is turning around this joint here. So, and then the point A has the velocity VA as a vector, and the point B has the velocity VB. And we know also from the dynamic, we learned already that if we have such a such a link or part of a mechanism turning around the point, let's say the joint O here. So, and here's the AB. And if we consider this line here from the O to B, from the O to B, so the tangential speed or the speed, linear speed, must be perpendicular to this line, because B is turning about the point O, and therefore it must be perpendicular to that. And we also know that B is equal, VB is equal. So from kinematic, we know, we learn in dynamic, VB is equal OB times omega. Omega is angular velocity, like here. So omega, you know, omega is equal d theta over dt, and d theta is the angle here. We can say this is the angle here, theta. So theta, differential theta, angle over dt defines the omega, and we can easily write the angular speed, calculate the angular velocity, and then linear velocity also for the point B. And for the point A, it's also same. It must be also the direction-wise must be perpendicular to the line OA, because for the time being or the instant, point A is turning, point A, let's say, is turning about the point O. So therefore, it must be also perpendicular to the linear motion. And also we can write BA is equal here, BA is equal OA times omega, same omega, because omega is same. Because this is a rigid body, and this rigid body is, that means the OAB is a rigid body, and OAB is turning about the point O. So therefore, each point on this rigid body has same angular speed. Okay, so what is here explained? Straight line instantaneous speed. Okay, this is instantaneous speed because it is changing. Here it doesn't change. If omega is constant, omega is constant, I mean the angular speed is constant. OB and OA is also constant, so that means the linear speed is not changing. But we will see later if we have in case of coupler like this here. So this is the crank we said, and this is the rocker, let's say, and this is the coupler here. Huh? So, and this coupler undergoes a plane motion, and since it undergoes plane motion, and all the kinematic parameters are instantaneous. I mean, for a certain a time, for instant. And straight line, okay, this is straight line instantaneous speed of a point here, of a point on for example, on the coupler. So, so direction here in this example, the direction is also already known. The instantaneous directions of the moment is like this. I mean, the linear motion is, you see the direction here. This is the direction, must be perpendicular to OB for the point B. And for the point A, the direction of the linear speed must be perpendicular to the line OA. Okay. So then linear velocity, okay, how can we define the linear velocity? We can define the linear velocity like, so V is equal dr over dt. What is dr? dr, the displacement. And time, dt is the time passed for this displacement. And this is the way how we calculate the linear speed, linear velocity like this. And we already learned that in dynamic. So here also we can write in a short interval dr, that's the displacement, differential displacement over dt, or dr is equal v dt, and so on. You remember these equations from kinematic. And we said, so there's an example here. So a hydraulic cylinder extends at a constant rate. Constant rate, that means the speed is constant, linear speed is constant. Since it is a linear actuator, also provides the linear motion. And to its full stroke of this stroke is here given 256 millimeters, and the time for that is 4 seconds. Determine the velocity of the rod end, and we already know we did it in our last lessons. So this is dr or ds dt over dt. This is the velocity, magnitude-wise the velocity, and this is here is equal, let's say 256 over 4, and this is here 64 millimeter per second. Huh? Is it correct? Okay, it's correct. So, okay, let's continue. Also, here an example. So, the velocity profile is shown here. So, the velocity profile, you see, it starts from 0 here. This is the origin. It starts from 0 and goes in that direction. So, this is the velocity time graph, and continue like this, and stopped. That means we accelerate. We start here and we continue with a constant speed. This is the constant speed area. Let's say, let's choose that here. So this is the part from 0 to 0.5 second. This is the second here. So we accelerate, we apply the acceleration. That means we increase the speed. Increase the speed from 0 to 9, and we continue with the speed 9, and then after we continue, let's say 3.5 seconds, and after 4 seconds, in total, we reduce the speed and bring, let's say, the gripper here we stop the motion. So the velocity profile is shown for a program robot here. This is the robot, and here the gripper, and determine the total displacement of the gripper. So how can we determine the displacement of the gripper? So what is displacement? So displacement, what means if you say displacement? So displacement, we already know that to define the speed here, we said speed is equal dr, let's say the displacement, let's say s over dt, dt. Okay, so then this is the displacement. So what is ds? How if we write it, ds is equal so v times dt, isn't it? dt. So v times dt is actually if we consider here, so this is the area here, v times dt.
We will take the integration, Hajam, right?
Yes, integration, but in this case we have a, let's say, the defined geometric figure, and we don't need the integrations. We can calculate the area of these geometric figures, and this is here. Let's say here for let's say this is the S1, and this is S2, and this is S3. So the area of S1 is equal, so 0.5 times 9 over 2 over 2. This is the area of this triangle, and the S2 S2 is equal, so here 9 times this is the here 4 minus 0.5, so 3.5. This is the time, and the speed is constant, is times 9. So, and then yes, 3 is equal, again, is a triangle here. So this is the area here, S2. And here, this is this area here, S3, and so on. S3 is equal also, here, this is the 1 second. So to stop the gripper, or to stop the motion, it needs, to start needs to bring, let's say, in nominal speed 0.5 seconds, but to stop needs 1 second. So therefore here we have to write 1 times 9 over 2. So if we add together, so we know the so the displacement, total displacement from 0 second to the 5 seconds. Okay, so let's continue. Any problem? Any question? No. Okay, so please pay attention for that. We start the motion from velocity 0, and come to the nominal speed 9 meters per second, and it happens in 0.5 seconds, and then we continue from 0.5 seconds to the 4 seconds. We continue with a constant speed. This is the 9 meters per second, and then after 4 seconds we start to stop. though, and it is stopped within 1 second. It takes 1 second, and we bring this speed from the 9 to the 0. And this total area is the total displacement robot undergoes. Okay, so then angular velocity. Let's talk about the angular velocity. Angular, linear, we said linear. We have still here the linear velocity. You see here the linear velocity, and now there's the angular velocity, omega 2. So omega 2, since it is the object is coded with 2 or numbered with 2, we say the omega 2. That means this rigid body, let's okay, no, not that. So this rigid body here is turning about the point, let's say O here, with an angular speed omega 2, and we know the omega 2 is equal, omega 2 here in this example is equal d theta over dt. This is the angle ratio over the ratio between differential angle and the differential time, as also here indicated, you see, shown here, to calculate the angular velocity. So, and also, what is the relation we already taught here, the relation between angular speed and the angular speed and the linear speed we already discussed, and you see here also we have the same, and we can write here VB is VB, the linear speed the point B is equal to omega 2. Of course, first the distance here, OB, length times omega 2, and this must be perpendicular to OB. This is very important, and this is also perpendicular to OA, because it's the linear speed of the point A, and here again the A is equal the distance here from the O to the A, OA, this is the distance times omega 2. Omega 2 is the angular velocity. Okay, so we learn actually what is the relation between angular velocity and the linear velocity of a certain point, which is turning about a point, and we know also the angular velocity. And for the linear displacement, you know, we start here, the angle, and we continue with a constant angle, or here the angle is changing over time here, you see, and this is the omega here, omega angular speed is here, especially omega is changing, theta is changing. So here we have constant is changing, the angle is not changing. That means actually no, omega is 0 here somewhere, because there is no change regarding the theta, if not change, so it must be 0, huh? So 0 over any time, it's also 0. So the angle has to change over the time. So, or we can write theta is equal, delta theta is equal omega times dt. So we can also calculate the angle, how much angle the moving part moved. So let's have an example regarding that. Here, what is our example? You see, there's a gear, and a gear rotates counterclockwise. Counterclockwise, that means so in that direction. So counterclockwise at a constant rate. That means constant rate. That means per times per angle. So it is constant. That means, so we can write in that way, which is constant. So that means, so the counterclockwise constant rate. Constant rate means omega is constant. So omega is constant. That means for a certain change of the theta, we have always the same time, delta t. So maybe in 1 second, 1 degrees, in 1 second, 1 radian, and so on. So this is constant, okay. So it travels from 300 angle in 5 seconds. So determine the angular velocity of the gear. So the travels angle is 300 degree in 0.5 seconds. So we have to calculate the angular, so the angular velocity. We know the angle, so let's say given is the angle, so theta in total is equal 300 degree, okay, and the time for that is t is equal 0.5 second, okay. So that means we know the in total the gear is turning, let's say around the point O here. Let's show that here, the point O here. This is the point. Gear turn about. So the O, and total angle is, let's say it starts from here, from 0, and total angle is 300, let's say somewhere here, not 360, somewhere here, comes from here. So from here to there, so this is 300 degrees, okay, and the time passed during this motion is 0.5 seconds. So let's calculate the angular velocity. So we know the angular velocity is, so the omega is equal delta theta over delta t. So delta theta, this is for us delta theta because the angle traveled, and here delta t, time passed. So then, but this is as degree given, huh? So degree. So we the angular, if we calculate the angular speed must be calculated in radian. So that means radian per second, huh? So we have to convert the degrees into the radian. So we know that the 300, so 300 must be divided by 100 and times pi, because 180 degrees 1 pi, and 280 is 260 is 2 pi. So then here we can calculate them. The angle passed in radian. So we can say here this is here this 0 is okay. Here we have 3, and we have here so then it is, so let's say 5 over 3 pi. Okay, so this is the angle passed, and this is time. So then we can say, okay, here's the angular speed is, where is my cursor here? Okay, let's use the red one, is better. So the angular speed is so equal 5/3 pi over 0.5 second. So, and this is here radian per second or 1/second. So this is the angular speed. Huh? Okay, so let's continue. Linear and angular velocity. We already actually discussed the relation between linear and angular velocity. What is the linear velocity and what's the angular velocity, and the relation between them. So you see the same example here, the position vector RB from O to the B, and the position vector R from O to A. Again, must be perpendicular here, and is also perpendicular to AB. So then this is the relation actually between linear velocity and the angular velocity. The relationship between linear and angular velocity, and the directions of V and the omega are always constant. That means direction. The omega can be clockwise or counterclockwise, and based on that, we can also, if the omega is counterclockwise, also linear speed is also counterclockwise. That means in the left hand. So then the magnitude, to calculate the magnitude, we need the length of the position vector and times the BB. The omega gives us, like here, according to these equations, V is equal our position vectors time, or the magnitude of the position vectors time the omega, or in vector form. So points have, this is important, points have linear velocity, and this point here have linear velocity, point B, or any point on this rigid body, or point A is in this example, and links have rotation velocity. For the links, total links, for the total links here, we can say it has angular velocity, not linear velocity, because we are talking not about a certain points, we are talking about a body, rigid body, and it has an angular velocity, rotation. Okay, so so here's the information about a note on radius, what is radians, and so on. So general, let's say take this one. Okay, general unit of the angular measure is the one. Radian is defined as angle when the arc generated is equal in length of the radius of the arc, like approximately, and so on. An angle in radians is like this arc over radius. So in practice, must be symbol that is used where appropriate, but the derived unit is 1. So inch, or I don't know, inch is not, we don't use millimeter, or generally they're omitted in combination with other units. So this is the picture here for that. So the example. So what is the problem here? What is to find? If the speed of point B here, so on, is 50 millimeter per second, determine the velocity of the point A if the length is moving clockwise. So the clockwise, that means, so it moves, let's use the pencil, and also the red one, because you can see that. So the moves clockwise. Clockwise means so in that direction, Okay. So the B is given already. B is equal 50 millimeter per second, okay. Velocity of the point A. So this is, we have to find out. So we know the directions. So if, since the rigid body turning clockwise, so that means the VB is like this. We know the direction. This is the direction, okay, perpendicular to, let's say, the OB. And the magnitude is also given. Let's assume that this is we use the scale and we can say this is 50 millimeter per second. So, and now we have to find the velocity of A, and we know the direction of A, that must be, so in that direction, it's perpendicular. Maybe it's not perpendicular. This is 60, and this, maybe it's like this. So this is the A, and we know this, the VA, this is the VA, okay, VA. And we know the direction, but we don't know the magnitude of the speed. And magnitude, how can we calculate the magnitude? So we know that this distance are also given. So we know that VB is equal, so VB is equal OB times omega, angular velocity. That means the angular velocity of this rigid body. And OB is known, VB is also known, omega is not known. So omega is equal, we can calculate omega. So omega is equal VB over OB, and this is equal 50 over 450, okay, 450, and it is equal, so this is 1, and this is 9, and this is 1 over 9 radian per second. So radian per second. And this is, let's say, nearly 0.1, so nearly, okay, and 0.1 radian per second. So how can we calculate the magnitude of VA? And we know also that VA is equal, we learned already, you know, the equation, the relation between the linear velocity and the angular velocity, OA, OA times omega. Omega must be same, angular velocity, because this is the rigid body, and rigid body has same angular velocity since it is turning about the point O. So then VA is equal, we know the direction, but we have to calculate the magnitude. So VA is equal, so the OA is already given, 200 here. So 200 millimeter times 0.5, sorry, 0.1. So then it is equal here 20 millimeter per second. So 20 millimeter per second. Okay. So So we have here an example, and we will also talk about. Then before we start that, let's make a 10 minutes break, and after 10 minutes we start. That means we start 10 past 14. So let's continue. Can you see the example?
Yeah.
Okay. So let's check what is given and what is to find. So the figure below or on the side illustrates a CAM mechanism. CAM mechanism, you see here, this is the CAM here. We shortly discussed it at the beginning of our lessons, but we will continue. I hope we will have time to talk about this CAM mechanism. You see, this is the CAM mechanism. It is turning around the point O here with a certain eccentricity. And this is the point where it is turning about. It's the turning point here, okay. Let's say this is the O turning point. And you see the diameter is changing. So this is the longest diameter here, since it is turning, and this is the shortest diameter here. So that means let's say this is the R1, and this is the R2, and the difference delta R is equal R1 minus R2 is the stroke actually. That means this part, this B, A, C, the links is, let's say, moving up and down. So, because of this eccentricity. Okay, so this is the mechanism. How does it work? So the point B is, BAC is also here fixed, so that means the turning about the point A, sorry. So what is given now? Let's talk, let's see. Okay, the figure below illustrates the CAM mechanism used to drive the exhaust port. So the exhaust port, this is the exhaust port here of an internal combustion engine. Okay, point B is a point of interest on the rocker plate. B, we are interested for the point B. Let's use another color for that. So point B, we are interested for that, point B. So point B is, okay, the point of interest on the rocker plate at this instant. So at this instant, this is also important, at this instant. So the CAM forces point B upwards at 30 millimeter per second. Upwards. That means the B is going, oh, no, I made a mistake. So B is, let's use the red one, is going to this. This is the speed of B in that direction. And also, it is perpendicular to the line here. This is the line here. You see BA, the line. BA, perpendicular. So the CAM force is point B upwards. So upwards. Oh, it is wrong. Upwards. So I have to remove it. No, not that. Okay. So Upwards means, okay. So in that direction, so in that direction, okay, upwards, and must be perpendicular to that here. This also known. This is actually VB, linear velocity of the point B. And the magnitude, we know the direction, must be perpendicular to BA, we already learned, because the length BAC is turning about the point A, fixed here. So therefore, we know the direction. We know also the magnitude. VB is equal 30 millimeter per second. This is also clear. Okay, it's given. So 30 millimeter per second. So draw a kinematic diagram and calculate degree of freedom. Okay, first we have to draw a kinematic diagram. So what is the kinematic diagram? This is kinematic diagram. Our kinematic diagram we have here. So turning around, and here we have the A here, and then the here, this is connected, same rigid body. So, and here we have a connections, but we don't know what's happened. So there is a, here is broken. So, and this is our point B. This is A, and this is O here, because it's also a turning point. The cam is turning around this point, and here is also a turning point. So turn these links BAC is also turning about this point A. Okay, this is the kinematic diagram. Calculate the degree of freedom. Okay, let's calculate the degree of freedom. So here, this is the 1. We have to number the links, 1, and this is 2, and this is 3. We don't know what's happened after C, and therefore we don't take into the consideration. So we know from our famous equations, degree of freedom is equal, F is equal 3 times n minus 1 plus, so minus 2 F1 minus F2. Okay. So let's here we have here 3 times how many links we have? 1, 2, 3. 1, 2, and 3. So 3 minus 1 and minus 2 times how many degree lower degree we have? We have here 1, 2. It is 2. Okay, 2 times 2. And we have also 1 high level contact here. This is this one here, and this is 1. Okay. And let's check it. Here we have 2, it makes 6. 2 times 3, 6, minus 4, minus 5, minus 5. So minus 4, minus 1, minus 5 is equal 1. That means the degree of freedom is 1. F is equal 1. So if the mechanism has the degree of freedom 1, so that means if we apply one motion, let's say from the cam, so it starts to move. 1 degree of freedom. So then let's calculate the angular velocity of the link BAC. BAC, the angular velocity. So to calculate the angular velocity of BAC. So how can we calculate the angular velocity of BAC? So we know the actual B, isn't it? The B is given already. B is so, and we can easily calculate BB. We write the equations. BB is equal or AB times AB times omega, angular velocity of the link BAC. So from these equations we can write omega is equal BB over omega. So sorry, AB. AB. Okay, AB, and it is equal, VB is 30 over AB. How much? The AB is given already 20, you see here. This is 20 here. So AB is 20 over 20. So then omega is equal 1.5 radian per second. So this is the angular speed for the links BAC, and it's also turning, so like this, so with this angular velocity about this point A. Determine the linear velocity of the point C. Okay, the point C, where is the point C here? So it must be, we know the direction actually, the direction must be perpendicular to the AC, and since it is turning in that direction, the counter, clockwise, so then it must be like this here. So this is BC. So how can we calculate the BC? BC is equal the length AC times C times omega. No. AC, okay, times omega of the links BAC, and then it is equal here AC. How much the AC? Let's see, AC is 15 times 1.5, and how much is equal 22.5 meters, so millimeters, sorry, must be, no. So let's write here 22.5 millimeters per second. Okay. So any question? No, then let's continue. Let's come to the relative velocity. So till now, we don't touch the relative velocity. We touched linear velocity and the angular velocity. Now we came to the point relative velocity. That means one relative to the others. So relative velocity means here the velocity of a point as seen from another point. So the velocity of a point as seen another point. So let's assume that somebody is sitting in this car. So this guy, let's have a Okay, the guy is sitting in this car. So, and let's do it in that way. It thinks somebody is here, and the other one is sitting here. On this guy is observing this one, and let's say checking the speed relative to this car. So this is not absolute speed, absolute velocity. This is relative velocity. That means the speed of this car relative to of the car. Let's say this is the car A, and this car B. Speed of the car A relative to B, or vice versa. So how can we write it? Can write in that way: velocity of B relative to A. So this is the way how we can show it. Velocity B relative to A, BA, or we can add a slash in between. But I mean, it is also, we can mostly use the VBA. That means B relative to A. So B relative to A. Okay. And then, so how can we write the exact equations here between A and B? So VB is relative. You see, relative VBA is equal VB minus as vector, VB minus VA. Or we can write VB is equal so VA plus VBA. And this is an important and interesting equations. So that means the velocity B is equal, absolute velocity of B is equal A absolute plus BA relative. So then in that way we can calculate the different point, the velocity of different points on a certain links or body. Okay, let's continue. With relative velocity. Here you see the relative velocity between 2 points, on a link is useful in determining velocity characteristic of the links. So especially the relative velocity of any 2 points. So the relative velocity of any 2 points on a link can be used to determine the angular velocity of that links. So the angular velocity, this is very important actually. So we can determine the angular velocity of this link. So assuming that points A, B, C, like here, A, B, C is not here, so A, B, C, lay on the link. The angular velocity can be stated as omega is equal VAB or over RAB, or VBC RBC over RBC, or V relative to VA relative to C RAC. So let's come to this example here. So how can we use this explanation here in this practice example? So here we have you see somebody is looking from this point A, in that direction, and observing the motion of the point B about the point A. So that means the speed, linear speed of the AB, of the point B about the point A, or relative to A, is VAB, like driven perpendicular to the line AB. So it is perpendicular here. So this is, this is here so it must be perpendicular to this line, like this here. It depends in which direction, in that direction or in that direction. So this is the relative velocity of B with respect to A. So the direction of the angular velocity is consistent with the relative velocity of the 2 points. The relative velocity of B with respect to A implies that B is seen as rotating about the A. So it's a very important expression. So B is, so the B is seen as rotating about the point A, like here. So therefore, the direction of the relative velocity of B as seen from A suggests the direction of the rotation of the link that is shared by the points A and B. So referring to figure, when VB is directed up and to the left, so the angular velocity of the link is the counterclockwise. So if it is in that direction, so then the angular velocity, the rotation is in that direction. So if it is, let's say, use the color again. So in that direction, so okay, this is the turning. And if it is in that direction, so then the clockwise, the rotation is the clockwise. So when VBA about the point A is directed up and to left, that means, and the angular velocity of the link is counterclockwise, like here. So, and conversely, when VBA is directed down and to the right, the angular velocity of the link is clockwise. So, and let's have an example here. This speed, what is it? The speed of point B is here 50 millimeter per second down, and the right, down to the right, determine the velocity of A relative to B. So we already learned it. We already learned it. So about the point, the relative about the point, point A. So how can we do that? Relative about the point A. So let's use it. This is the speed, and the B is given. The speed of point B is 50 millimeter down to the right. That means, so in that direction, perpendicular to OB. So like this, perpendicular. So, okay. This is VB. Okay. Now the question is, so of course the speed of A is also in that direction. We know that. We know the direction. It is also perpendicular to the AOA. So there are different methods to calculate the speed at this instant. So one of them is the graphical method, and the other one is the analytical method, and we will talk about. But now first we think about the analytical method. Okay, of course we can also talk about the we use the graphical method, and then of course we can calculate using the analytical method. So this is BA. Okay, so then the question is determine the velocity of A relative to B. A relative to B. So that means V A relative to B. So, and that means, so VA is equal or determine the velocity of A relative to B. AB. Okay, then we have to write the equations B B is equal, so BA plus how was it? B so no, this is where I will change relative to A relative to B means, okay, let's have to change that. Let's change it. Okay, so that have to write in that way. So okay, BA is equal BB plus BAB. A relative to B. A relative to B. Okay. So this is the question we have to calculate. We don't know that. We don't know that. But what we know actually is very interesting. Now you have to follow exactly what we know. We know the magnitude of the speed B, velocity B, magnitude and also direction. Let's draw like parallel to that. Way of graph, use the graphical way. So this is parallel to that. And let's have this point here somewhere. And let's indicate the value, the speed dB. So this is our VB, okay. VB. So we know also the equations of we know the direction of the A, isn't it? Direction of A is, you see here. Let's use another, also that one. Direction, this is the, it must be parallel to that one. So, okay. So parallel. We know the direction. We don't know the direction, but we don't know the magnitude, but we know the directions. Okay. So then, what is the direction of VAB? Do we know that? Direction of VAB. That means B is, let's assume that B is turning around the point, about the point A. So it must be also perpendicular to AB. Must be, where is it? Must be perpendicular to AB. And has to go to this point here, the end of this VB. So then perpendicular, that means, so this is like this. So perpendicular, let's have like this. So this is the line. This is the line here, perpendicular to the line AB. AB. So, and this is here our VA. VA. We have here the vector polygon. So VA and VB. This is VAB. So VA is equal VB plus VAB. So, but no, it was in that direction. No, I made a mistake. Sorry. VA. V must be okay. VA in that VA must be in that direction. Okay, and this is also in that direction. VB is equal VAB. Okay, let's change here that. Must be like this. VA also in that direction. Okay, VA is equal. So VB plus must be perpendicular to that, counterclockwise, go in that direction. Okay, this is also correct. So the PB is equal. Actually, the question is determine the velocity of A relative to B. Actually, it must be B relative to A. This is wrong. I have to correct it here. B relative to A. So this is now correct, relative to A. Okay. So then it's correct, and I have to change. A is equal, okay, VA, VB. So VB is equal, let's correct it also. So then there's a problem with the question. VB is equal VA plus VBA, B about the point A, then it's correct. So this is VBA, VBA, this is relative speed, and this is we are looking for. So, okay, then you see here, this is our VA, is always given. VA is equal, like here. So VB is equal VA plus BA. So this, I have to also correct it, VBA. Let's VBA, where is it? VBA, okay, VBA. BA. Okay, so now this is correct. And this line is, you see, this line is perpendicular to that one, to AB. So I'm sorry, I cannot say draw the line correctly, but you should you have to take in you have to see like this, that the AB is perpendicular. This line is perpendicular to AB. Since B is turning, so if we say relative B relative to A, we assume that B is turning about the point A. So therefore, the relative speed or velocity B relative to A must be, the direction must be perpendicular to the line AB. Okay, so then we know the, actually from the problem given, we know the magnitude and the direction of VB. VB is given already, okay, and we have to calculate the VA and VBA. So then making this graph or drawing this graph, graphically we can calculate the VA and VB, and we find the VA and VB. We know the directions already. The VA must perpendicular to the line OA, and VB must perpendicular to OB, and VBA must also perpendicular to AB. So using all these facilities or all these, then we draw this triangle, and consists of vectors VA, VB, and VBA. So then if we use a scale, we can graphically find out so the value of the VA and the value of the VBA. And if we know the VBA, so we can calculate also the omega, the angular speed of the AB about the point A, since we know the length here. The omega AB is equal, so VBA over AB, length AB. Okay, like here, where is it? Here we set VAB, RAB, and VBC, RBC, and VAC, A relative to C, or A relative to B, and so on. Okay. So then let's come to the velocity analysis, relative velocity method. So we will use the relative velocity method here. So, and the 2 points on a rigid body can only have a relative velocity, 2 points, let's say A and B. So as an example, we use here the crank rocker mechanism, as you see, is crank rocker mechanism. And of course, we know that the point A undergoes the motion about this point. This is a circular motion, and B is also as a circular motion about the point A. But what about the AB or any point on the coupler AB? This is general plane motion. So it has partly it is linear motion, partly rotary motion. So therefore, we will use this method and relative velocity method to calculate the speed of any point on the coupler. So 2 points on a rigid body can only have a relative velocity perpendicular to the link that connects them. So if we want to calculate the relative velocity, relative B to A, relative B with respect to A, so this relative speed must be perpendicular to AB. So the motion of B as seen from A, so from A we see the, as somebody is observing the motion of B about the point A. So it is also a circular motion. So checked or observed from the point of A. So this is very important definition or the explanation we'll use. So here you see the graphical velocity analysis, relative velocity methods. So here we have a crank rocker mechanism, and you see the crank has the velocity VA. We use the graphical relative velocity method, the graphical velocity analysis. We use the graphical method. So this is the VA and must be perpendicular, like you see here, must be perpendicular to the link A0O, A, and also VB is also must be perpendicular like this here. You see here, perpendicular to the length B0B. If it is turned in that direction, if in that direction, if in that direction, okay, then this one here. And the relative velocity B with respect A was also perpendicular to that line here. AB, because B relative to A, the motion of B relative to A. So this is the direction. So that means, so if we analyze the velocity for a crank rocker mechanism, for any mechanism, so we have to consider the points, which type of motion undergoes, and what is known regarding the magnitude or direction, or both of them. Here, for example, we have we have written in vector form here. This is our VA. This is this here, VA. So the VA. And VB is VA. We have to know VA as magnitude and as direction in order to calculate the others. So then, let's say we have here the direction of VB. You see, this is the direction of VB. This is the direction of VB, like this here. This is the, we don't know the magnitude for the time being maybe, but direction we know. And we know also the direction of VBA. So this is the direction of VBA, like this here. And if we know the magnitude and direction of the VA, so then by drawing the line, the related line, like here, let's say the parallel to that one, and also parallel to the, okay, this one here. So then by graphically we can find out the VB and VA, VBA, and if you use a certain scale for VAB, so then using this scale we can calculate. This is the magnitude of dBA, and this magnitude of the dB. So this is the way how can we calculate the velocity, the relative velocity, or using the relative velocity, how can we calculate the other velocity? For example, any point on this coupler, speed of any point on this coupler, and later on the acceleration, let's say the c. So, okay. So I think it's enough for today. So then you have an example here. You have to work on that. The crank and connecting rod of a theoretical steam engine are 0.5 meter, 2 meter long, respectively. The crank makes 180 RPM in the clockwise direction. When it has turned 45 degrees from the inner dead center position, that means inner the limiting position, determine the velocity of the position of the P, and angular velocity of connecting rod, velocity of the point E on the connecting rod 1.5 meter from the cadmium pin, and position and linear velocity of any points G on the connecting rod which has the least velocity relative to the crankshaft. You work on that, okay? So that was today. Any question?
These parts are included at the exam?
Velocity included, yes.
Okay.
But we learned actually, not more. We will learn more, but this is the part we learned, yes, it is included.
Okay, thanks.
So then, have a nice week, and good luck for in the exam. Bye-bye.
Sir Hojam, I have a little question.
Yes, please.
The exam will gonna be, we have to write explanation, we have to, or have to send the paper, or it's multiple choice or something like that?
Exam will be multiple choice. That means you will select the answer, you will calculate and select the right answer. But after exam, so I express once more. So after exam, within 15 minutes, you have to scan the exam paper and send to me via the mail. Okay.
Nice. Tamam.
Okay.
Tamam. Good.
So.
That's also the same for mechatronics components?
Not the mechatronics, not the same, because mechatronic it doesn't need any calculations. You will have the question multiple choice, but in static and theory of machines and the design too. The paper you use for the solution of the question, you have to scan and send to me within 15 minutes after exam.
It will be by email, right? Thank you.
Yes, by email. Yes, okay.
Thank you so much.
So bye-bye.
Bye-bye.
Hojam, can you please upload the slides of this course so we study to the exam, because we don't have any background to study from.
For the theory of machines?
Yes.
But I recommended the book, and I use this book. All this information you have in this book, and this is free of charge. I mean, you can upload from the internet.
I know, Hojam, but the book is so expanded. It's not like the slides.
No, I will not use the slides. Sorry for that. But you see the book here. I'm showing now once more. I select all these examples from this book here. Okay. Mechanics and machines and mechanism, applied kinematics analysis. So, okay.
Hocam,
Yes,
can I ask a question about design 2 homework?
design 2 homework. Well, so what is the question? But I asked the question to talk about yesterday. You didn't say anything.
Oh, hocam,
So what is the question?
actually I finished it, but the last 2 questions are upload something, and I don't know how can we upload them.
Yes, Hudam, it's not clear and it's not, I think, in our field of study.
Yes,
Ah.
it's our
Uh,
over study.
What about the attempts? You can attempts many, or let's say that
No,
3
no,
times.
no, Hudam.
No,
The,
hocam,
the,
the
the
only
last two
question.
questions.
So what is your problem?
Hocam
Exactly.
son iki soru bizden bir grafik gibi bir şey çizmemizi istiyor da.
Ha.
Yani
You
böyle
couldn't do it.
elle yapılacak gibi bir şey sanırım. Hani seçme şansımız yok onu. O son iki soruyu silme şansınız var mı ya da değiştirme şansınız?
Okay, let's don't do the last don't answer the last 2 questions. Then I will evaluate without last 2 question. Okay.
Okay.
Is it
Hocam,
okay?
that's meaning, I think it's over 260, so it's adding 20 points to each grade, I think.
Well, I will check it. I don't know for timing, but you can assume that I will evaluate your homework without taking into account the last two questions. Okay.
Okay, thank you.
Doctor,
Okay.
can you a little extend the deadline, because this week we had exams. Deadline for machine design too.
You mean the extended time delivery time?
Yes, the homework machine design too.
Well,
A little.
so
not
I
too
can
much.
do that. I can do that. I mean, but I think that you work and you prepare yourself for the exam, and this is the reason why you have to finish before the midterm.
Okay.
But okay, I can expand it. No problem.
Thanks a lot.
Okay, you are welcome. So now bye bye, huh? I have another lesson.
Hocam, one last thing.
So what's the question?
For theory of mechanics homework, how can I submit it? By email or until we come back to face to face?
By email.
By email.
Yes, your paper. The answers. I mean, written on a paper. You have to scan and send to me by email. Okay.
Okay.
After finishing the exam within 15 minutes, not late.
How the date for the homework or the exam?
Yes, you will answer this. You will have a multiple choice question, and you will
He's asking about the homework, not the exam.
not homework. Okay, per email. Per email. I explained already. That's per email.
Oh, okay.
Okay.
Okay. Thank you.
So then, bye bye.